next speaker is Jakob Moritz. He will talk about modular superpotential from singular divisors. Take it away, please.
Thank you very much, especially Marcus and Gary for having me give this talk here. It's a great pleasure to speak in particular here because it's just an opportunity to just basically talk to the entire community. So that's exciting. And I'll talk about upcoming work that I'm currently writing up with Naomi Gendler, Menki Kim, Liam McAllister, and Mike Stillman. And the title of this work is Modular Superpotentials from Singular Divisors. So before I start giving details, let me draw your attention to this figure that I've drawn on my opening slide. This is a phase diagram of a family of Calabi-Yau threefolds. And one feature that I hope you will understand by the end of this talk is how the edges, the infinitely many edges of this diagram drawn in red, correspond to the infinitely many terms in a Fourier expansion of a modular superpotential. But what's perhaps more important than the fact that we get to a modular superpotential in the end is how we get there. Namely, it'll turn out that almost all terms in the superpotential will be generated by wrapping Euclidean branes on singularities of a certain kind that I will introduce to you. So by studying, in particular, this example here, we will be able to draw general lessons about what are the rules of the game for fermion zero-mode counting on Euclidean D3-branes. So here's an outline. I don't think I'll need a long introduction for this audience, so I'll be brief. I will just basically use this to set up my notation and tell you what the setup is that we will actually study. Then I'll actually go on and we will study D3-brane instantons wrapped on singular divisors. In particular, we'll study this one example. And then in the following section, I will explain to you how to use this information to construct a modular superpotential, something that you can generalize beyond the example that I'm giving, and then I'll conclude. So let's start. The setup is pretty simple. We compactify type 2b string theory on a Calabi-Yau threefold X. And furthermore, we define a holomorphic orientifold involution that I'll call I, and its fixed points in X are the O3 and the O7 planes. Now, an important feature of such compactifications is that the four-dimensional EFT has n equals to 1 supersymmetry, and in particular comes with light chiral multiplets called Calabi-Moduli. I will denote them T sub I. Their real parts parameterize the volumes of a homology basis of 4 cycles in X. And the imaginary parts are axions that you get by dimensionally reducing the 10-dimensional 4 form C4. Now, as you probably all know, the 10-dimensional gauge symmetry of C4 implies for us that the axions, so the imaginary parts of the T's, cannot actually receive a potential to any order in perturbation theory. And we can extend this to in the following way using holomorphy. The superpotential can depend on the entire chiral multiplets Ti only through instanton corrections. So famously, the superpotential takes the form I'm writing here. There's the famous constant part, which is classical, and everything else is non-perturbative. And what are these non-perturbative effects? They are instantons, and they are you can think of them as Euclidean D3-branes wrapped on holomorphic 4 cycles, i.e., effective divisors. Now, one quick look at this equation, and you'll be able to appreciate that in order to understand the vacuum structure of such models, we will need to understand how to compute Euclidean D-brane instanton corrections to the superpotential, and this plays a crucial role in modular stabilization, say in KKLT, the large volume scenario, but also variants thereof. And in particular, in order to make progress, we need to understand how the counting of fermionic zero modes on Euclidean D3-branes goes in generality. And at first you might think, isn't this a closed subject? Isn't it well known how to do this? And indeed, for smooth divisors, the counting of fermion zero modes on Euclidean D3-branes was already developed by Witten a long time ago. And in particular, zero modes take values in the cohomology groups of the structure sheaf of D. And as a consequence, if you have a smooth divisor, then if it's moreover orientifold even, connected, and rigid, it will contribute to the superpotential. Here, rigid means that the Hodge vector, i.e. the dimensions of the cohomology groups written above, just take the simple form 1, 0, 0. And in particular, the arithmetic genus, which is the alternating sum of these dimensions, is equal to 1. Now I want to close this introduction by recalling that a crucial starting point for Witten's observation is that the world volume fermions transform as sections of the spin bundle that you construct out of the normal bundle to the divisor D inside of X. So that concludes my introduction. Now let me go to talk about D3-brane instantons wrapped on single divisors and study our example. Now, a key point is that if there are point-like singularities in D, we don't actually see a reason to distrust the derivation given by Witten, even though he assumes from the start that divisors are smooth. However, for normal crossing singularities along a curve C, there's a problem. So here I'm assuming that the normal crossing curve is a P1, and I'm drawing a picture of how this might look. So it's a cartoon, of course, where the divisor essentially cuts itself along a locus of complex codimension 1, and this is a P1 here. In this case, the starting point is ill-defined. You cannot define a normal bundle at the singular curve C. And what's perhaps more shocking is that such divisor singularities turn out to be an extremely common feature of Calabi-Yau compactifications. And I will give an argument why this is so later. But before I do so, let me give a more precise version of our main point. I will give you a physics proof that Witten's result actually carries through upon replacing our divisor D with a smooth fiducial divisor. I'm going to denote it D sub res, called the log resolution of D. Now, what is this? To obtain a log resolution, one finds a birational map between our space, our Calabi-Yau variety X, and our divisor D, and a fiducial threefold Y, and a fiducial divisor D sub res that is one-to-one away from our singular curve C, in such a way that our divisor D sub res is actually smooth. And how do we do this? Or what will we do in what follows? Our strategy will be to give a physical incarnation to such a map here by using so-called flop transitions, and show that this prescription actually does give the right answer in our concrete example. So what's our example? We define a Calabi-Yau hypersurface X by the vanishing of the anti-canonical polynomial in a toric fourfold V, which turns out to be a P1 times P1 fibration over weighted projective space 1, 1, 2, and which is defined by the following scaling weights here. So x1 to x7 are homogeneous coordinates, and we orientifold our fourfold V. We orientifold our threefold X by the involution that's induced by ascending x1 to minus x1. Now, a particularly important feature of this Calabi-Yau threefold is that the divisors D4 and D5 that are defined by the vanishing of the homogeneous coordinates x4, respectively x5, and intersect those loci with a Calabi-Yau threefold in V, are indeed smooth, and they also generate a superpotential following Witten's argument. Let's now go on and study this example in more detail. The Kähler cone, so H01 is 3, so the Kähler cone is a three-dimensional cone, and it has 3 walls, so it's a simplicial cone, where the effective curve classes, which are just chosen to be the unit vectors, shrink to conifolds. And in particular, the Kähler cone is just, so I've chosen my coordinates such that the Kähler cone is the first octant. So the 3 Kähler parameters are constrained to be bigger than 0. However, upon sending, so in particular, upon sending T3 to 0, the effective curve C3, written up there, will shrink to 0 volume. Now, importantly, you can actually continue to negative values of the Kähler parameter, and upon doing so, the geometry will undergo a flop transition. So I'm not going to give you any details of how to prove this. It's slightly non-trivial, and there's an upcoming work where we will explain how to do this rather generally. But for now, I'm going to ask you to just believe me that this is so. Crucially, in this way, by following through the flop transition, one generates a new Calabi-Yau x tilde, which is topologically distinct. And here is the phase diagram that you get from this. I'm showing you a two-dimensional cross-section of the three-dimensional calacone, of the two calacones, to be precise. And it looks as follows. The upper left triangle is the calacone that we started with, and it's connected via a codimension 1 wall, where the volume of the curve C3 shrinks to a different phase, whose calacone I'm going to denote K sub x tilde. Now this new calacone has two further walls, and along these two walls, the divisors D4 and D5 that I defined before shrink to zero volume, and in particular, they shrink to points. And this means, among other things, that these two divisors are actually generators of the cone of effective divisors. Now, you can go on and similarly pass through the other two walls that the calacone of our variety X has, namely sending T1 or T2 to negative values. And in this case, our Calabi-Yau X again undergoes a flop transition. However, there's now a very crucial difference. Flopping either of these two curves produces Calabi-Yaus that are isomorphic to X. So they have, in a suitable basis, the same triple intersection numbers and second rank class. And this also appears in this feature also appears in these works that I'm citing here. However, they are not identical in a trivial sense. Namely, making the isomorphism between the two manifest will require to choose a new basis of the lattice of curves, and it turns out to be given by the columns of this matrix lambda that I'm defining here. And what this means is that the group that you get by exponentiating this matrix lambda is a monodromy group of Kähler-modular space. So the curved lattice undergoes monodromy transformations. And we can use the action of this monodromy group to actually find all the geometric phases. And here's how this goes. We start out with the two calacones that I showed you in the beginning. And now we act on these two cones with the monodromy group. So this is the starting point. I'm now going to act with lambda to the 1 and -1. I'm going to add -2 and 2, -3 and 3, and I'm going to iterate this all the way to infinity. And this is how you get the phase diagram that I showed you on my title slide. Now it's particularly important to look at the exterior edges there, because the divisors that shrink there are the images of D4 and D5 under the monodromy group. And since D4 and D5 are in fact generators of the effective cone, so are all their images under the monodromy group. And in fact, it's a little bit simpler even, because so D5 can be obtained by acting with a certain group element on D4. So in fact, the generators of the effective cone are just simply given by the monodromy orbit of a single divisor class D4. But now recall that D4, which is equivalent to D0 here, and D5, which is equivalent to D1, satisfy Witten's criterion for a non-vanishing superpotential contribution, at least as long as you evaluated it in the original phase X. So now, by continuing from X to X prime, which is isomorphic to X, one finds that the divisors D1 and D2 contribute to the superpotential evaluated in that phase. So there are two options. Either the entire set of generators of the effective cone all contribute to the superpotential, or the set of contributing divisors must jump across a flop transition. And this latter possibility we can actually exclude. Namely, by holomorphy, the instanton expansion of W of the superpotential is trusted when divisors are large. W depends only on divisor volumes, not on curve volumes. And flop transitions only involve shrinking of curves and not of divisors. So this is sort of by definition. Therefore, the superpotentials of the evaluated in the two phases are related to each other by a rather trivial form of an analytic continuation, i.e. you don't have to resum any instantons to get from x to x prime. And therefore, if any of these divisors dk contributes in any of those phases, it must actually contribute in all phases. So this concludes the proof. And we conclude in particular that infinitely many divisors will contribute to the superpotential. Now, seemingly that's a problem, because this seems to be at odds with Witten's result. If you compute the arithmetic genus of the generators of the effective cone, and you do this in the original phase x, you find that only for 4 different values of k, these divisors have arithmetic genus equal to 1. In all other cases, it's actually smaller. So what's going on here? Now, as you can probably imagine from how I've told the story so far, it'll turn out that the divisors dk that are precisely outside of this range from -1 to 2 all have normal crossing singularities in the original phase. And we can turn this around by saying that, for instance, the divisor D2 develops normal crossing singularity by going through a flop transition between 2 isomorphic phases x and x prime, at which, say, the second generator of the Mori cone of our first phase collapses. Now, in order to see this, one first notes that if a divisor D intersects a conifold curve at an isolated point, then near that point, the divisor simply looks like C2. But crucially, the flop transition will modify the divisor. So on the left-hand side, I'm showing you divisor that's just the C2 and a P1 curve that intersects it transversely in one point. And on the right-hand side, I'm showing you the divisor topology on the other side of the transition. And now the P1 turns out to be contained in our divisor. So the intersection number goes from +1 to -1. And the divisor topology is now C2 blown up at the origin. Now, the divisor D2 that we started with is a little different. It intersects the shrinking curve not once, but twice. So this means that locally, near the intersection points, we get actually 2 sheets of C2. And what the flop does is it glues them together along a P1. So here's my my attempt to draw what's going on to embed this in 3 dimensions, which is not quite possible. But the crucial feature is that both of them will have a blow-up P1, and it'll be the same one. So they intersect each other transversely along this blow-up P1. Oh. And the crucial point is, therefore, that flop transitions create normal crossing singularities of divisors. Now, let me give you a status report of what has happened so far. First, we've argued that the physical zero mode counting must actually be invariant under flop transitions due to holomorphy. And then we have seen that there exist actually infinitely many examples of generically singular divisors, which you can smooth via going through a suitable series of flop transitions. And therefore, the following strategy works. You can count fermion zero modes in the appropriate phase where the divisor D is smooth. And there you can just use Witten's result, but then you can extend this result to all of the phases. Now here's an important fact: 2 geometric phases that I'm going to call x and x prime, and for this they don't, and here they don't have to be necessarily isomorphic to each other. If they are related by a flop transition, it means they're birationally equivalent. In other words, there's a one-to-one map between those two away from the shrinking curves. And we therefore see that the flop transition relating these two manifolds x and x prime actually constructs for us the map phi we've used in the beginning to define what we mean by a log resolution. And therefore, we essentially prove our claim. Now, I should tell you a little bit about what we expected, how generic this feature is going to be. Because at first you might think I'm just constructing a particularly strange example here just to find an application for this prescription. But and maybe you can already anticipate this. Most divisors are actually expected to feature normal crossing singularities in precisely this way. And the reason is that it's generally expected that the extended Kähler cone of a family of Calabi-Yau threefolds is expected. So it's expected that it actually contains exponentially many in H11 distinct phases, and they are all related to each other via flood transitions. And now it's obvious that almost all divisors you can choose will intersect any given flood curve with an intersection number that's not -1, 0, or 1. And for anything that's outside this range, by going through a flood transition, you will either create or undo a singularity, a normal crossing singularity, just in the way that I showed you up there for conifolds. So let me now move on to to the final section. Let me construct for you modular superpotentials, or actually I will precisely construct one, but you can generalize this prescription easily. So
about 4 minutes.
Thanks. That's all. That's perfect. So first of all, to open up this section, you might expect that just simply by a naive analogy to the SL to Z duality of type 2B string theory, that for the n equals 1 compactifications feature also duality symmetries involving the Kähler moduli. Say something where a divisor goes to 1, a divisor volume gets inverted. After all, the volumes of divisors are couplings too. And in this case, the superpotential would need to transform covariantly under such a transformation. So it would be modular in a sense. And indeed, superpotentials like this have been found in the literature, for instance, long ago by Donagi, Russell, and Witten. And our example is actually is a perfect candidate for such a superpotential, because I've argued that there's an infinitely generated effective cone, and all generators contribute to the superpotential. So there are definitely infinitely many terms in the instant on expansion. And now we can actually make progress, because so we have infinitely many contributions to the superpotential. Each come with a one-loop Pfaffian in front that's hard to compute. But we note that all contributing divisors are actually related by the monodromy group, which in a sense is a symmetry group. And this implies that we can actually compute the superpotential up to one overall normalization factor, which is then still hard to compute. So I'm going to just call it A of Z and tau, where Z are the complex structure moduli and the dilaton. Everything, so that we can just factor that out and perform the sum on the exponentials as written here. Now, this series that I've defined here actually defines a Jacobi theta function. So this is indeed a function that has modular properties. I should say there's a subtlety in the dependence of the one-loop Pfaffian A on D3-brane position moduli, but I'm going to skip over this for now. If you can ask me about it if you're interested. So let me start again and make it more precise. The superpotential features modular properties, and and in particular, there's a strong weak coupling duality that involves sending this tau3 to -1 over itself, and you see tau3 is related to the volume of an effective divisor. And this transformation property, I would say, suggests in a relatively precise way the existence of a weak-strong coupling duality that involves indeed the inversion of an Einstein frame divisor volume. Now, it would be interesting to do phenomenology with these kind of superpotentials, but at least in this particular example, the superpotential only has simple roots. So there are no Minkowski-Susy vector in this example. So it's hard to say what kind of vector could exist in general. But maybe one can find other examples along similar lines that do have such vacuum. So let me conclude. So first of all, we've used analytic continuation of a 4D superpotential in order to show that zero-mode counting on divisors with normal crossing singularities along P1s is governed by the cohomology of the log resolution. And in this way, we expect that this result allows us in principle to count fermion zero modes on any effective divisor. Now I've argued for this using one example, and it has this is an interesting example. It has infinitely many phases. It has an infinitely generated effective cone. It has an infinite order monodromy group that relates its generators. So many infinities here. And in particular, we can use the action of the monodromy group to construct modular superpotentials in a way that I believe is novel. And here's a possible future direction that I already alluded to before. It would be interesting if one can construct non-perturbative superpotentials like this that can actually be used to find vacuum at strong coupling. And this is all I have to say. Thanks for your attention, and I hope we still have time for questions.
Thank you, Jakob, for a nice talk. Let's see if you have questions. Let me ask one. You use the fact that the zero-mode counting is invariant under the flop transition. Mm-hmm. Is this statement true for n equals to 1 compactifications, say F theory or orientifold constructions?
Yeah. So the argument that we used was what we used was holomorphic of the superpotential. So this should be valid in n equals to 1 compactifications. So in particular, so the reason is that if you go if you have a calicone and you go through a flop transition, then you can do this transition arbitrarily far out in the phase of the calicone that's defined by this flop transition. And as you move out there, all divisors become parametrically large. So the instanton expansion of the superpotential converges arbitrarily well. So you should be able to just move through this transition to continue the superpotential from one phase to another.
Mm-hmm. Okay, so thanks. Next, we have Francisco.
Hi, okay. Can you see?
Yes.
So
but you're not Francisco.
Yeah, I don't look like Francisco, but we are all together. So nice talk. I have just a quick question. So you're saying that you can generate in the end several contributions to the superpotential from these singular divisors. Mm-hmm. But you know that this is true when there is no flux. And
yes, absolutely.
Yeah. So did you check that you can ensure this in a way compatible with the cancellation of all Fried-Witten anomalies? Because they require you to turn on half-integer fluxes, which you try to cancel with the B term.
Exactly. Yeah. No, you can cancel Fried-Witten anomalies by turning on half-integral flux on the wall volume of the O7 of the 7 branes, and then cancel this with a half-integral B field. Exactly. Yeah.
Right, but can you do it for all of them with just one choice of the B field?
Yes, I believe so. But let me check that again. But I believe that's true. Yes.
Okay. Thank you very much.
Okay, Timo, and then Ling.
Hi. Just to be sure, these flop transitions that you use, they do not change the number of space-time filling D3-branes or chi over 24 more generally of the fourfold. Did I understand correctly?
Yes, that's correct. Yes. So you can something I haven't. So I'm leaving out many details here, but something you can show is that the O3 planes and so if you apply the monodromy group, the 7 brane divisor is mapped to itself. And likewise, the O3 planes are mapped to themselves. So this maps one orientifold to another, and these orientifolds are the same. So in particular, the D3-brane tadpole is the same.
Okay, thank you. The D3-brane tadpole, and also the number of D3-branes. So the specific distribution into. Okay, thank you.
So in particular, you can move. So you can move away the D3-branes wherever you want them to be, and these maps are birational along. So it means that they're defined everywhere except along curves. So I don't know what exactly happens if you tune your modular for them to be exactly on those curves. But as long as you don't do that, they definitely should stay the same. Yes.
Thank you.
Ling.
Yeah. Hi, Jakob. Thanks for the great talk. I had a very naive question. So I remember in this context of heterotic compactifications, these multi-superpotentials, they have this kind of beastly Witten vanishing theorem, something that kills off essentially all the contributions that are non-zero for, in that case, curves, and all within the same curve class. So in this case, you are computing it for a single divisor, right?
Right. Yes. Yeah. So there's only a single. So there's a crucial difference between curves and divisors, in that if you have a rigid divisor, it means there's only one section of the corresponding line bundle. So there's only one representative of this.
Okay.
So there's no possibility for there's no clear possibility for something like a Beasley Witten cancellation to occur. And I believe that in all cases where we can use dualities to relate vanishing theorems from the heterotic string to type 2 to type 2b, F theory, I believe that usually corresponds to loci of exceptional gauge enhancement, and then you can, I think you can understand the vanishing of superpotential contributions through that as well. And none of that happens here. So I believe these are actually non-zero superpotential contributions.
Okay, thanks.
We have a question from Fernando.
Yes, it's me. Is this Fernando?
Yes. This is the real one.
Well, you said it. Okay, well, thank you for the talk. It's very interesting. So I was wondering in the old days about the superpotential in the case of SL2Z was supposed to be a modular form of degree 3 or -3 or something. In this case, you have a bigger modular group. So do you know exactly the transformation of the superpotential? And if so, how does that, what does that imply for the rest of the superpotential, including fluxes and so on, that may not transform?
Yeah, so that's an excellent question. So something for this particular setup, we have not turned on any bulk fluxes because we didn't know. Maybe one can make an argument, but we didn't know how these would transform under our monodromy group, or more generally under these strong weak coupling dualities. I think it's conceivable that they just stay the same, but it's also just as conceivable that they transform in a non-trivial manner. So it'd be really interesting to understand how that works. Yeah, maybe one can use that, how they general knowledge about how the superpotential should transform to get to these, but I'm not sure. But yeah,
but that would be interesting to see the whole.
Yeah,
the whole superpotential should transform in the same way. And also, when you were looking for critical point, you said that you didn't find solutions of W equal to 0, and so you didn't find supersymmetric solutions. That's what you meant?
Yeah, so let me be a little bit more precise. So
that was my question.
Oh, sorry.
No worries, no worries.
Okay, so you have this Jacobi form, and it depends on two combinations of Calabi parameters, namely the antisymmetric combination of T1 and T2, and the third Calabi parameter. And there's up front you have this exponential dependence on the symmetric combination. So if you see first of all the Jacobi form has only simple zeros, so you cannot find solutions to dw equals to w equal to 0. So if you just evaluate how dw with respect to z and tau 3 here of this form, you will find solutions. However, w, so the VEV of the Jacobi form is non-zero there. So then you still have this exponential runaway potential for the symmetric combination. And you might be able to do better by including fluxes and have a small w0. You could, for instance, imagine that's a hybrid stabilization where we stabilize the symmetric combination using KKLT, but everything else is at strong coupling. But this would still be difficult because vacua for which capital DW is equal to 0, but W itself is not 0. They depend, of course, on the Calabi potential, and we don't know much about the Calabi potential at strong coupling.
Yes, but on the other hand, if you have concrete modular properties, I think in general, the fixed points under your duality group should be extreme of the potential at least.
Yes, indeed.
Then maybe giving you some hint on where the extreme, the minima are, because the fixed points are for SL2Z, exactly the two of them, but for more bigger groups, I think you can identify them. I think automatically you know that the scalar potential has to be invariant, and then these fixed points have to be extreme of the potential. That will give you already a lot of information, I guess, independent of the scalar potential.
That's an interesting argument. So if you just you're probably just referring to this this transformation here, right?
Yeah. But then,
So for instance, z equal to 0, tau 3 equal to I, right?
Mm-hmm.
Yeah, it'd be interesting to check if one can prove that these are actually vacua. But certainly, if I take our monodromy group and ask what are its fixed points, then that's at infinite distance. So these are just like the runaway vacua or dual thereof.
Mm-hmm. Okay.
Yeah, I'll think about this.
It's very interesting. Very interesting. Thank you.
Thanks for the question.
Earlier, Andreas had a question. Do you still have the question?
It was the same as Fernando's question. So,
okay. All right. So then we'll go to Irina.
Yeah. Yes. Very quick. Thank you for the talk.
Hi, Irina.
Yeah. Hi. So just very quick. So just to understand the relation to the Morrison and Kawamata conjecture that the cone should be finitely generated. So when you say that it's infinitely generated, it's before taking into account the duality group. So actually it's only generated by a finite number of non-isomorphic classes, right?
Yes. So you could. So we're working in the universal cover. So you don't have any orbifold fixed planes in modular space. So you can always, in terms of just counting inequivalent phases, yes, you just have two inequivalent phases. So this is not in contradiction with that conjecture. Okay.
And you have not found any example that could be in contradiction with that, right?
No, in fact, I think whenever we've seen such infinite series of flops, and I think this was also observed by Brody et al. In one of the two papers I cited earlier. It was just always found that whenever you have an infinite series, they're just like all the same. It could in principle be still compatible with the conjecture if you have like any number of them and you just move cyclically around, right? But that I've never seen an example where that actually happens.
Okay, thank you.
Okay, so I don't see any more questions and we are also running late. So let's thank Jakob and also Max for the wonderful talks. We will continue